Okay, let's unpack this. Imagine everything you thought you knew about how science progresses was fundamentally, beautifully, well, wrong.
Hmm,
Today, we're not just diving into a classic book, we're stepping into Thomas Kuhn's The Structure of Scientific Revolutions.
a huge one.
Yeah, a work so impactful that our sources call it one of the great books, one that literally changed our understanding of the sciences forever, and it just might change yours too.
That's absolutely right. Kuhn, um, he was originally trained as a physicist, actually.
Oh, interesting.
And he published this book back in 1962. A fascinating time, really. Physics was, the queen of the sciences then.
Right, the atomic age.
Exactly. Deeply tied to the Cold War, the atomic bomb.
Right.
It's quite remarkable to think about how his observations from that era still resonate, even today.
Even though science looks so different now.
Right, now it's dominated by biotech, information science. Computer simulation means even, experiment is not what it was, as one source puts it. So our mission today is to cut through, decades of debate and really give you the core insights into Kuhn's revolutionary ideas.
Okay, let's do it. So if you're like me, you probably grew up picturing science as this, I don't know, steady, straight line.
The standard view, yeah.
Each new discovery just adds neatly onto the pile of knowledge. But Kuhn looked at that development by accumulation model and basically said, hang on a second.
He really questioned it.
He'd argue that trying to pinpoint exact moments like when was oxygen discovered or who first conceived of energy conservation, those are, quote, simply the wrong sorts of questions to ask. What's so wrong with asking that?
Well, Kuhn really pulls back the curtain on how science textbooks, for instance, can be, and this is his phrase, systematically misleading.
Misleading how?
They create this neat picture, this illusion of a seamless, cumulative march forward. They make it seem like past scientific ideas, think Aristotelian dynamics or phlogistic chemistry, were just simple error.
Just mistakes we fixed.
Right. Mistakes we've since corrected. But Kuhn argues they were coherent. They were valid science within their own frameworks, you see.
Ah, okay. So not just wrong, but different.
Exactly. It's a profound shift in thinking. Science doesn't just add new pieces to the puzzle. It fundamentally transforms the entire structure, the whole picture.
Wow, that's a big revelation. So if science isn't just about piling up facts, what is it, according to Kuhn? He brings in this idea of normal science.
Yes, normal science.
And this isn't the flashy Nobel Prize stuff you see in movies, right?
Yeah.
It's described as research firmly based upon one or more past scientific achievements, almost like puzzle solving. What does that actually mean for the average scientist working day to day?
Normal science is incredibly focused. Really focused.
Yeah.
Its most striking feature, Kuhn says, is how little they aim to produce major novelties, conceptual or phenomenal.
So not looking for breakthroughs.
Not typically, no. Instead, the goal is really to add to the scope and precision with which the paradigm can be applied. Think of it as refining an existing framework, deepening the understanding within it.
Okay, like filling in the detail.
Exactly. This involves sort of three main activities. One is determining key facts with more precision, like, say, stellar positions.
Right.
Another is matching facts predicted by the theory with experimental results, like demonstrating Newton's second law with an Atwood machine in the lab.
Classic physics experiment.
And the third is articulating the theory itself, applying it to new kinds of problems, which, Newton himself did, and only sparingly, but others really refined.
So what happens if an experiment doesn't work out as expected during this normal science phase?
That's key. If an experiment doesn't yield the anticipated result, it's typically seen as a research failure by the scientist, not a flaw in the fundamental theory, the paradigm itself.
Ah, so the scientist blames themselves, not the theory.
Pretty much. It's truly puzzle solving within the established rules of the game.
Okay, so if normal science is puzzle solving within a framework, that brings us straight to the framework itself, what Kuhn called the paradigm.
The big one.
Yeah, the big P word. He famously admitted he kind of lost control of this word because it just exploded, everyone started using it. But what did he really mean by paradigm?
That's a critical question because you're right, the word is everywhere now, often misused. Kuhn clarified that paradigm operates in, two key ways, two main senses.
Okay.
The first is what he called the global or sociological sense. This is like the entire constellation of beliefs, values, techniques, and so on shared by the members of a given community.
So like the culture of that scientific field.
Exactly. It's the invisible glue that binds a scientific community together. These are people who have undergone similar educations and professional initiations. They share a common understanding of what science is, what counts as a good question, a good answer.
Got it. And the second sense?
The second sense, which Kuhn actually considered deeper, is the local or exemplar sense. These are more like concrete problem solutions.
Examples?
Yes, actual examples or models that scientists learn from. Think of the classic problems solved in textbooks. These often replace explicit rules as the real basis for solving new puzzles.
So it's not just about learning the rules from a book, it's more like learning by doing, by seeing examples.
Precisely. Think about how students learn science. You don't just memorize equations, do you?
Not effectively, no.
You learn by doing those problems at the end of the textbook chapters. That's where you pick up the tacit knowledge, the unspoken understanding, the intuition.
Like how to actually use the formula.
Exactly. For instance, learning Newton's second law, ESMA, isn't just knowing the equation. It's learning to see how that law applies to a free-falling object or a pendulum or coupled oscillators. It's about learning to see situations as like each other, recognizing the pattern.
That makes a lot of sense. So a paradigm doesn't just dictate the problem scientists work on.
No, it also provides the very criterion for choosing problems that can be assumed to have solutions.
So it tells you which problems are worth tackling because they should be solvable within the current system.
Right. And this helps insulate the community from problems that don't fit the mold, problems that might just be distractions, which, Kuhn argues, is one of the reasons why normal science seems to progress so rapidly. It maintains focus.
Okay, so normal science is focused, puzzle solving within a paradigm. But what happens when the puzzles don't fit?
Well, while normal science aims for stability, it inevitably, almost by definition, generates what Kuhn called anomaly.
Anomaly, something weird.
Something contrary to law-like regularities, more generally contrary to expectations. Something the paradigm didn't predict or can't easily explain.
Does an anomaly immediately disprove the theory?
Not always. It isn't always a direct refutation. Sometimes it's just an outlier, a result that sits there, kind of nagging people, like Robert Brown's observation back in the 19th century of pollen grains jittering randomly in water.
Brownian motion.
Exactly. It didn't make much sense at the time, but it just sat there. It only really clicked decades later with the development of molecular theory.
So sometimes anomalies just wait for a better explanation. But what happens when they don't go away? When they keep piling up?
Right. When these anomalies became persistent, when they strike at the core of the paradigm, and when they become, well, profound, they can trigger what Kuhn calls a crisis.
Crisis? That sounds pretty dramatic for science.
It can be. Our sources mentioned Wolfgang Pauli, the physicist, famously feeling that physics is, again, terribly confused, just months before the new quantum theory emerged. That's a sign of crisis.
And are there other signs?
Yes. One key symptom of a crisis is often a proliferation of versions of a theory. People start tweaking the existing paradigm in different ways, trying to patch it up to account for the anomalies.
Can you give us some historical examples where we really see this crisis playing out?
Oh, absolutely. History's full of them. Think about Ptolemaic astronomy. For centuries, it was the way to understand the cosmos, the Earth-centered view. Right. But it entered crisis because its complexity was increasing far more rapidly than its accuracy. They kept adding circles upon circles, epicycles, to make it match observations. Copernicus eventually described the system as a monster. It just got too clunky, too messy.
Okay, so complexity, overwhelming accuracy. What else?
Well, in 18th century chemistry, you had the prevailing phlogiston theory. It tried to explain combustion, but it really struggled with the discovery of new gases, and especially the really puzzling fact that materials often gained weight after burning, which seemed impossible if something phlogiston was being released.
That is weird.
Yeah. Lavoisier, who later proposed the oxygen theory, even recorded in a sealed note to the French Academy that he felt something was wrong with the current chemical thinking. That's crisis talk.
And Newton, even Newtonian physics faced this.
Indeed. Newtonian physics, the bedrock for centuries, faced its own crisis towards the end of the 19th century. There were problems like trying to understand motion relative to the hypothesized ether that supposedly filled space.
The Michelson-Morley experiment.
That was a huge anomaly, yes. And also the inexplicable tiny precession, the wobble, in the orbit of Mercury's perihelion. It just couldn't be quite squared with Newton's laws. These were cracks appearing in a very solid foundation.
Okay, this is fascinating. So the crisis builds. It's not simply science proving something wrong and moving on then. Our usual picture often involves falsification. You find evidence against a theory, you discard it, How does Kuhn's view on abandoning a theory differ?
It differs quite fundamentally. It's precisely not just about falsification, though anomalies play a role. Kuhn argues very strongly that a scientific theory is declared invalid only if an alternate candidate is available to take its place.
Only if there's a replacement ready.
Exactly. This is crucial. It means the decision to abandon an old paradigm, an old theory, is always simultaneously the decision to embrace a new one. You don't just throw out a theory because you find a problem with it, leaving a vacuum.
You need something better to jump to.
Yeah. Right. You throw it out because you have something that looks like it might work better, something to replace it with. It's like switching horses mid-race, maybe, not just abandoning the race altogether.
So when that switch happens, when they embrace the new candidate, what is a scientific revolution fundamentally in Kuhn's terms?
It's nothing less than a reconstruction of the field from new fundamentals.
Yeah.
It's radical. It's not just finding new answers to old questions.
It changes the questions too.
Oh, absolutely. New questions, new methods, new standards entirely. It's about handling the same bundle of data as before, but placing them in a new system of relations with one another by giving them a different framework.
Yeah.
The facts might seem the same, but their meaning changes.
This is where that idea of a gestalt switch comes in, right? Like that classic optical illusion where you see the duck.
And then suddenly you see the rabbit. Yes.
Kuhn argues that after a revolution, scientists, quote, do not see something as something else. Instead, they simply see it. They literally work in a different world. How profound is that change? How literal is different world?
It's incredibly profound. And Kuhn meant it quite seriously. Consider Lavoisier again. He saw oxygen where Priestley had seen dephlogisticated air. It wasn't just a relabeling.
It changed everything else.
Yes. To see oxygen, Lavoisier had to change his view of many other more familiar substances, as well acids, metals, combustion itself. This meant, in a very real sense, Lavoisier worked in a different world.
Give us another example.
Okay, think about the pendulum. Before a certain paradigm shift in mechanics, probably in the late Middle Ages or early Renaissance, there were literally no pendulums but only swinging stones for the scientists to see. Just a stone swinging back and forth.
Right.
But someone like Galileo, influenced by newer ideas about impetus and motion, saw that swinging stone differently. He saw a regular, repeatable motion with properties that could be measured and described by laws. And poof, the pendulum as a scientific object was born.
Wow, even core concepts change.
Absolutely. Think about mass. Newtonian mass is conserved. Einsteinian is convertible with energy. That's a fundamental shift. The very meaning changes. Kuhn says the conceptual web whose strands are space, time, matter, force, and so on had to be shifted and laid down again on nature whole. It's a complete rearrangement of the fundamentals.
That's wild. So if the very fabric of their scientific reality changes, if they're seeing different things working in different worlds,
Yeah.
this must lead to communication problems, right?
Exactly. This leads directly to what Kuhn called incommensurability.
Incommensurability. That's a fancy word.
It is, but the idea is that communication across the revolutionary divide is inevitably partial. They can't perfectly understand each other.
It sounds like an impossible situation for scientific debate.
It is challenging, and Kuhn points out it's actually a familiar fact of life to any working scientist who's tried to bridge a deep conceptual gap with a colleague from a different specialty or viewpoint.
So how do they argue if they can't fully communicate?
Well, when paradigms clash, the debates aren't really resolved by logical proof or direct comparison with data in the way you might think. Why? Because the fundamental premises, the starting points, the ways of seeing are different.
So logic doesn't work?
Not in a straightforward, deductive way. Instead, Kuhn says, it becomes a process more like persuasion, trying to convince the other side.
Like a political debate, almost.
In some ways, yes. Even shared values that scientists hold dear, like accuracy or simplicity or scope, can be differently applied by proponents of competing paradigms. What looks simple to one might look ad hoc to another.
So how do they bridge this gap, even partially?
Kuhn suggests scientists have to become translators. They have to try and understand how the other group sees and says things differently, figure out the mapping between their world and the other world.
That sounds difficult.
He calls it a challenging, even threatening process, because it forces you to potentially question your own fundamental assumptions. But it's what allows scientists to vicariously experience, to some extent, the merits of an opposing view.
Okay, so they try to translate, persuade. But here's a really interesting point from our sources. Even if someone is persuaded by the arguments for a new paradigm,
Yes.
that translation need not be accompanied or followed by conversion. You might understand it intellectually, but not fully adopt it.
Exactly. Kuhn noted this. Our sources mention that people, particularly those who came of age scientifically under the old paradigm, even if they become intellectually convinced by new theories like relativity or quantum mechanics in their middle years, might find themselves unable to internalize it and be at home in the world it helps to shape.
They can't quite make the leap emotionally or intuitively.
It seems so. It's often the young and rising naturalists, the next generation, who fully convert and truly operate within the new world.
Which leads to that famous kind of bleak quote from Max Planck, right?
Ah, yes, Planck's famous lament. A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that is familiar with it.
Wow. That sounds almost brutal, but it really highlights just how deep these paradigm shifts are, doesn't it? How hard it is to change worlds.
It really does. It paints a picture of scientific change that's so much messier, more human, and more discontinuous than the clean, linear narrative we usually get.
Okay, so if these changes are so profound, transforming entire scientific worlds, making old ways almost unintelligible, why aren't they more obvious? Why isn't this revolutionary story the standard story of science we learn? Why do we tend to miss them?
It goes right back to those science textbooks we talked about earlier, and scientific education more broadly.
They hide the revolutions.
In effect, yes. Textbooks are almost always produced in the aftermath of a scientific revolution. Their purpose is to record the stable outcome of past revolutions and to present the basis of the current normal scientific tradition. They teach you how to do science now.
So they smooth things over.
They effectively rewrite history. They select and often distort past scientific work to make it appear as if it was always leading directly, step by step, towards today's understanding. They make the previous paradigm look like a stumbling precursor rather than a coherent system in its own right.
So they make the revolutions invisible.
Precisely. This is why, for example, the modern concept of a chemical element is often attributed back to Robert Boyle in textbooks, even though his definition and the context in which he used it weren't really the same as how we use element after Lavoisier's chemical revolution.
They make it look like Boyle was just an early, slightly less clear version of us.
Exactly. This whole textbook approach makes science appear largely cumulative, which obscures the true, often quite chaotic and revolutionary process of fundamental change.
That's almost disorienting to realize how much shaping goes into that story. Okay, this brings us to another really deep question then. If science isn't this steady march towards truth, if it involves these messy revolutions and incommensurable worldviews, why is it still seen as progressing in a way that, say, art or philosophy or political theory might not seem to progress in the same way?
That's a fantastic question, and Kuhn tackles it head on. Part of the answer, he suggests, lies in the eye of the beholder.
Meaning
Meaning that within any single ongoing scientific community operating under a shared paradigm, successful work is progress by definition. They are solving the puzzles set by their paradigm more effectively.
okay, so progress is relative to the current paradigm.
To some extent, yes. But there's more to it. A key difference for mature sciences, Kuhn argues, is their unparalleled insulation from the demands of the laity and of everyday life.
They work for themselves, basically.
Largely, yes. Scientists primarily work for and are evaluated by their peers within that specialized community, people who share the same values, assumptions, and standards derived from the paradigm. This intense internal focus, this insulation, drives incredible efficiency in puzzle solving. They're not constantly justifying themselves to outsiders.
And maybe counterintuitively, this self-contained nature also influences how revolutions themselves are perceived, even from within.
Absolutely. Think about it. When one paradigm triumphs over another in revolution, the victorious group, the ones writing the new textbooks, will never say that the result of its victory has been something less than progress. Of course not.
They won. Their way is better, obviously.
Naturally. And this view is reinforced by the way scientific education shapes our historical perception, as we just discussed. The losses as well as gains in scientific revolutions, things the old paradigm might have explained well that the new one struggles with, initially tend to get overlooked or forgotten. This reinforces that linear view of constant improvement.
So Kuhn is suggesting we might need to rethink what progress even means in science.
He is. He suggests we might have to relinquish the notion that changes of paradigm carry scientists and those who learn from them closer and closer to the truth with a capital T. That idea of science marching toward one final true picture of reality.
So what does he propose instead? If not towards truth, then what?
He proposes an evolutionary view, much like Darwinian natural selection. Science doesn't necessarily progress towards some predefined ultimate goal or truth. Instead, it progresses away from earlier, less effective ways of understanding and problem solving.
Away from, not towards.
Exactly. Think of evolution. It produces organisms better adapted to current environments, not necessarily heading towards some ultimate perfect form. Similarly, Kuhn says, later scientific theories are better than earlier ones for solving puzzles in the often quite different environments to which they are applied. They work better for the problem scientists are currently facing.
So it's progress in terms of problem-solving ability within a context, not necessarily progress towards absolute truth.
Precisely. And it's important to note this isn't necessarily relativism, saying any theory is as good as any other. It's a different and arguably more historically accurate understanding of what scientific progress actually consists of. Better puzzle-solving tools for the job at hand.
Wow. Okay, this whole deep dive has really shifted my perspective. It shows that science isn't just this neat march of facts,
No, it is dynamic.
but a dynamic, often tumultuous process of revolutions where entire ways of seeing the world get transformed. It's a powerful reminder that knowledge isn't static. It's living, it's evolving, and it's deeply tied to the communities, the people who create it.
Absolutely. Kuhn's work really forces us to look beyond those simplified textbook narratives and appreciate the messy human, but also deeply intellectual process that truly drives scientific discovery and fundamental change. His insights are still profoundly relevant for understanding why science operates the way it does and why, despite the revolutions, it remains such a uniquely effective engine for generating knowledge.
So maybe a final thought for you, our listener, to mull over. The next time you encounter a new scientific theory, or maybe even just read about a scientific fact you thought you knew, ask yourself, what world, what paradigm am I actually stepping into? And what existing assumptions, what shared ways of seeing might be shaping what I'm even able to perceive or conceive of in the first place?